I want to challenge people, and I want to apologise first if I offend any of the tree physiologists, because I am going to challenge you, because I think you are part of the solution, and and based on my ignorance, I may be challenging you a little too hard. So let's see how we go. But I'm going to come back to this question: can biogenic manufacturing save the planet? That's a big claim, and I want to argue that and see if I can convince you that forestry and algae can solve this problem. I'll give some introductions to why algae is important. I'll talk about the importance of biogenic products, and this is where we need to start changing industries. I'll look to opportunities with the construction industry, and then I'll wrap up with some incentives. And I think the incentives is the most important part, so I want to make sure there's plenty of time for that. So a bit of brief background. Where do I come from? I come from Australia. I come from the University of Technology in Sydney. I head up a research institute. It's 13 years old, the same age as Czech Globe, but we're a lot smaller. We're only 100 people in size. And the group that I'm going to be presenting data from is the Algae Biosystems group. We have other people in other areas. Now, the context. Australia, over the last 3 years, has been massively hit by climate change. We have so much evidence of it. In 2019, we had mega blazes across Australia. We had 8 months of fires. We had cyclones hitting Sydney. Sydney is not in the tropics. We don't get cyclones. We have cyclones now. And we have floods in towns and cities that have survived for 140 years. So things are changing in Australia. I don't need to convince this audience, but one thing I will show is a paper that just came out in Science about 2 weeks ago. And this talks about tipping points. I, in my past career, was a coral researcher, a polar researcher. We even worked in freshwater macrophytes. But I used to tell people about these ecosystems that were damaged and destroyed. We've now got evidence that we've passed tipping points for 5 of these ecosystems. So coral reefs, I know, are gone. The Greenland ice sheet is collapsing and melting. We've got permafrost that's re-emitting methane. The Antarctic ice sheet is fracturing faster than ever, and the Atlantic current is slowing and getting more dilute. So these tipping points have happened. This is 1.1 degrees, and we're trying to stay under 1.5. And you can see how many other ecosystems are going to be tipped once we hit 1.5. So things are urgent. So what do we need to do? Unfortunately, we don't need to plant more trees. Trees are important, but we're going to run out of space to plant the trees. And I want to argue why we need to use the trees to make biogenic products, to stick them into buildings. This is what the talk's going to be about. So we need negative emission technologies or carbon dioxide removal. And for Christian's sake, I will be defining a lot of my terms. Down here, this is a pyramid of importance. We need to spend most of our time avoiding emissions and removing problem emissions. The least amount of our effort should be spent in offsets. And this is what I'm going to be talking about, reducing and replacing. So this is our trajectory. If we do nothing, business as usual, we'll just keep making more and more CO2. This is 2022. We need to bend the curve the same way we did in COVID. What we're going to have here is electrification. This is going to be a massive reduction in our putting of CO2 into the atmosphere. This part down here is the important part. This is existing CO2 that's in the atmosphere that we have to remove. We have to have technologies to remove it. And by 2050, to get to a net zero emissions, we've got to remove huge quantities permanently. And this is the problem. Permanent removal of CO2 is not easy. The technology is not there. So, what are the technologies that I'll talk about? Carbon dioxide removal can be either carbon capture and use or carbon capture and manufacture. I prefer carbon capture and manufacture. People understand you're making stuff out of that atmospheric carbon. Carbon capture and storage in the petrochemical industry is code name for enhanced oil recovery, which is essentially just burn the coal, burn the gas, capture the carbon, stick it back underground, but don't store it, remove more petrochemical products. So we've got to avoid CCS and we've got to use carbon capture and use technologies. Some of these technologies, so this is direct air capture, is extremely expensive, but it's going to be a long-term storage mechanism. These are some of the technologies that exist now for negative emission technologies. They're biological, chemical, and physical. And you can see their prices across here. Some of them, forestry, at $5 to $50 a tonne of carbon, are very effective. That's why forestry is really important right now for carbon capture, because we can actually make money. In Europe at the moment, we've got €70 is the cost of a tonne of carbon. In Australia, it's $30. So looking at these industries, which ones can you actually make money? By using biogenic production, you don't need to use a carbon tax to actually make the money. You actually make products. So here you've got $500 to $600 a tonne for the Climeworks technology. Very, very important, very exciting, but it's going to take another 10, 20 years before it's cost effective. We need to create these short-term sinks that can save and remove atmospheric carbon, maybe for 10, 20, 30 years, and then we get these other technologies through. So I've gone back to this image a few times. So what I'm proposing is the carbon's emitted, it's captured by a tree, a seagrass, a forest system, goes into a biogenic, a biorefinery, we make stuff and we store it in the buildings. This is a new way of short-term storage. So what I've done here is to try and show you the importance of short-term storage. That's the image I showed you before, and I was telling you all about this blue section. I've inverted the image and reversed it, and here it is here. So you can see that 2022, we've got to start capturing, and by 2050, we've got massive amounts. This is a diagram from the Oxford Net Zero principle. And what they're saying is it's going to take us 30 years to get the technology to do the important long-term storage. But in the short term, we've got to do heaps of this stuff, the short-term storage. And that's where forestry and other systems come in. So some of the work we're doing back at UTS is we're doing some short-term algal-based net emission technology. So we've developed, and this is on a street next door to our university, this is a shipping container-based carbon capture unit. So it can run as direct air capture and makes algal biomass. You can stick it next to a generator, captures the carbon, makes biomass. You can put it in an anaerobic digester, takes out the CO2 from the methane, makes algal biomass. These are types of technologies that exist now. So let's now talk about the construction industry. I could have picked any industry. We're involved in food and beverages, we're involved in textiles, but next week I go to London and I'm talking with Writers, the largest architectural firm on the planet, to start getting them thinking about where in the construction industry we can actually stick carbon. So the construction industry represents about 30% of global emissions. Cement is 8% by itself. Building the buildings, running the buildings, this is where all the carbon costs come. So what we need to do is we transform buildings from being carbon sources to sinks. And this is going to be transformational for the planet. So another pyramid. So stuff at the top, we shouldn't use. The stuff at the bottom, we can use heaps in buildings. So this is all net zero. This is all wood timber products. Up the top here, we've got coppers. These things are 10,000 kilograms of CO2 per cubic metre of production. These are our targets. We need to remove the carbon from these if we can, and obviously copper, zinc, we can't put carbon into them. But some of these products I'll talk about, we can actually decarbonise and take the fossil components out. So some of the targets we've got up here in the 1,000 kilograms of CO2 per cubic metre of vinyl flooring and ceramic tiles. We can stick carbon into those compounds, and this is going to be major savings in the construction industry. Similarly, we've got smaller targets down in the 100 kilograms, bricks, polyethylene, polyurethane, polypropylene. All of the plastics, we can essentially replace components. We can't replace completely. So what we need to do is we need to start thinking about biogenic sources of carbon. Now, forestry is a massive one of these, and it's really exciting, and I want to see how the forestry industry can change from lumber production to bioproducts production. Also, sedges, grasses, bamboo, seaweeds and microalgae. I'll talk a lot more about the microalgae opportunities. Essentially what we have is we have a biorefinery. We take the feedstock in, It's a refinery that creates these products at the other end, and we stick them into society. So the carbon goes into the stuff that we use, as opposed to paying for it to stick underground. So some of the things that I challenge the forestry industry to start thinking about is some of the bioproducts they can have apart from lumber. So lignin-based foams. I'll talk more about foams that are really important for the construction industry. Pulp installation, phenolic adhesives, polyurethane for cross-laminated timber, even bioethanol. All of these can be done, but I think the problem is, as I've heard at this conference, the forestry industry is conservative. It's not thinking about the future, and I want to challenge it for that. So what do we do at C3 in these industries? We work, as I said, we work in the food and beverages, pharmaceuticals, energy, ag, textile and fashion, and also in the construction industry. We use algae as a platform to transform industries, to remove fossil components and to turn it into a sustainable system. Very briefly, why algae? Algae, it's massive genetic diversity, 300 to 400,000 species. You can see us down there, this is the tree of life. And so bacteria are off the tree of life. This is all higher organisms. Humans are down here in the metazoans. All of our trees are up here in this taxa. Every other coloured taxa is an alga taxa. So there is massive genetic diversity. Therefore, there is massive molecular diversity. We can create endless products from these. I see basically the opportunity with microalgae as being a biofactory. We can change the environmental conditions to get the different metabolic products that we want to meet what the industry needs. There's virtually no organic product that we can't create using this technology. The way that we do it is either through raceways, tubular bioreactors. It's interesting, on the way here 2 days ago, we drove past this place. So this place is called Ekaduna. It's down in northern Austria, and it's a massive chlorella producer in Europe. Macroalgae, on the other hand, you can grow it on land, you can do coastal harvesting, or you can do it in offshore production. So, staying on the topic is, can biogenic carbon save the planet? What I want to talk about is the simplicity with which we can actually make change. Now, this is a diagram I use when I'm talking to the textile industry. What I've got here is two pathways. This is the evil pathway, this is the future. And this is all standard production. So what I'll run through is just briefly how you make a sustainable fibre. The old way was you extract fossil-derived carbon, you crack it, you put it through chemical processes, you make a monomer, you make a polymer, you make a pellet, you extract the pellet into a fibre, you spin the yarn, and you make your fabric. The alternate way is you grow corn, you extract your sugar, you grow the yeast, you make the monomer, make a polymer, and everything's the same. This idea means you don't change industry. You change the raw material that goes in, and you allow the fossil industry to die while our industry grows. For microalgae and macroalgae, we just stick it up the top there, and we make the monomers straight out of the algae. That's the advantage of the feedstocks we've got. Now briefly, what can we do in the construction industry? Working with riders, they show me all these cross-sections of buildings, and I had no idea how much plastic goes into construction. Every single one of these layers through here has a function, and it's usually moisture removal, moisture prevention. All of these barriers can be replaced, and we can turn these into carbon sinks. Buildings aren't just bricks and mortar. You can replace, and I'll talk about biobricks, you can create and store carbon in the biobricks as well. But you've got films, membranes, injection molded fixtures, foams, fibres for carpets. All of these things are bioplastics, and they can store carbon. Biobricks, wall panels, concrete fillers, composite materials, these are all other ways that we can stick carbon into buildings. Briefly, rigid biofilms. Foam is the greatest use in construction. I had no idea that they are the greatest user of it. They use it for thermal barriers, ceiling, flooring, all of it. And there's huge numbers of plant-based alternatives already. So this is a way that we are sticking carbon now into buildings. This is some of the foam that we've made back at UTS. Construction membranes. So polyurethane, polyethylene, polypropylene. We can make algal-based equivalents of these and stick carbon into those buildings now. This technology exists. Carpet tiles. This is a company in Australia. The company's called Interface. They've been at the forefront of making modular floor panels that are recyclable, and the fibre in the carpet and the backing in the carpet can be bio-based, and it's not petrochemical based. So this is removing the vinyl floors at 1,000 kilograms a cubic metre. This is now carbon negative. This is a huge opportunity in carpet tiles. Finally, with BioBricks. This is a company over in the US. For any of the algal people in the group, you'll recognise Coccolitha florens. So that's the alga, and it makes these little discs, calcium carbonate discs, and they collect the discs and make construction bricks out of it. So that's net negative emissions going straight into buildings. Okay, what I want to finish off is how we can change society to incentivise to do this. I hope you're convinced that we can stick it into buildings. I hope you're convinced that the technology's there. It's just that there's no dollars at the moment. So my question again is, can biogenic manufacturing save the planet? Yes, I think it can, because it's going to reduce the carbon intensity of goods and services. The bioeconomy is going to drive the decarbonisation of these industries. We've got plenty of biomass. The biomass is of good quality, but the problem is we can't afford it. The cost is not working at the moment. And so we've got to create a market that values carbon and incentivises buildings to be sinks, not sources. So Europe's done. You guys are leading the field in this space. So the Green Deal has a component in it called Carbon Border Adjustment Mechanism. This is a fantastic tool that is going to prevent evil Australian companies, and Australian companies are panicked at the moment because we make lots of products we send to Europe. We use carbon-intensive processes, but as soon as they hit the border here coming to Europe, the price is going to go up. So our companies in Australia are going to try and become more carbon negative so that we can get our products into Europe. So in 2024, you bring up that border, and so all industries are frantically trying to work out how to adjust the carbon border adjustment mechanism. The good thing for me is CBAM is going to create an opportunity to invest in technologies that's going to do short-term storage, because we cannot do long-term storage, as I said before. We need another 20, 30 years. And so the investment's going to go into the partial credits, and this is how products are going to become carbon credit units that we will deal in. So what's a product carbon footprint? That's essentially a chair, and it costs 19 kilograms of carbon. Now in the past, ethical purchasers would go around and go, oh, okay, it cost me 38 euros, but it's 19 kilos of carbon. I'll choose one that's got less carbon. We have this technology, but we need to use this technology more effectively. So product carbon footprints exist, and they use a technology called life cycle analysis. So we have to understand where the carbons come from and where it goes to. And the real challenge is understanding the whole production chain, and not a lot of information is available here. So Carbon Trading 101, you need to understand 3 scopes of your carbon. Scope 1, 2 and 3. Scope 1 is the carbon that's absolutely in your product that you've made. Scope 2 is the electricity, the cost of carbon that's used to drive it. Scope 3 is the upstream and the downstream. So these parts here, we don't know how much carbon's gone into either of these parts, we just know the middle. And most of the systems ignore the upstream, which is the hardest. So for example, Siemens, they have 65,000 suppliers in 145 countries. Every single one of those you have to have a carbon product footprint for to understand where the carbon's going. This is a massive challenge. So product carbon footprints aren't accurate. They're averages. Each product, they just take an industrial average. They don't work out the individual product. And so this is where it's not driving industry to select a biogenic carbon product as opposed to a fossil carbon product to drop their individual cost. Once this mechanism comes into place, and once industry can do it, they will be picking the biogenic carbon as opposed to the fossil carbon. this is my next step in my European visit. So after I visit writers in London, I go across to Germany and I'm meeting up in Estonium. So Estonium is an industry organisation, and me as a photosynthesis guy doesn't really fit in there. But I've got a background in carbon trading and we're one of the founding members of this. So Estonium is going to give the globe, and this is open source technology, a digital verifiable carbon footprint. So every company can talk to individuals and work out what their carbon footprint of their raw materials are and not disclose it to another competitor. And this is the key thing. Industry won't touch this if everyone else knows what their carbon footprint is. So this is a very, very exciting technology. Uses blockchain, and basically the individual who owns the product declares what their carbon is, it's verified, and then it stays in the blockchain. It's not disclosed to anyone else. So essentially, I think Estonium and the carbon border adjustment mechanism is going to give us the tools to use biogenic carbon much more effectively than offsetting with forestry. So just quickly to show you how it works, imagine you've got a factory in Germany, it emits CO2. That's captured, it goes into one of these carbon capture units, you make biomass. An independent verifier says that that much carbon went into that much biomass. That is in the blockchain. That biomass then moves to a biofinery, the biomass goes into the biofinery and you make a wall panel. That goes into a building, that independent verifier proves that blockchain is correct. So now we've got a blockchain from that molecule of carbon to that building. And now the building can claim a carbon credit for 10 years while that building holds that carbon. This is going to transform the construction industry. So what we've now got is we've got sinks that are both natural sinks, which we've been talking about at this conference. So emissions go into a tree, you pay for the tree and you get a carbon sink. Now the emission can go into a tree, go into a biorefinery, go into a bioproduct, go into a building, and you get a carbon credit. All these different technologies are going to work. Now this is in honour of Christian. I've talked all about the importance of fixing a whole bunch of carbon, but it's going to cost a lot of nitrogen and phosphorus. It's absolutely true. So everything I'm talking about here is circular economy. I want to use sewage, wastewater, not fertiliser that we need to be using for food production. And all of these systems, nobody cares whether a wood panel or a wall panel came from nitrogen and phosphorus, it's got sewage in it. I even am planning to have clothes made with sewage. So long as we're not eating it, we need other sources of nitrogen and phosphorus, not food-based. So that's where the circular economy comes in. Finally, the opportunities for you guys. I suppose I've seen this over the last 5 years and it's transformed my institute. My institute is a bunch of biologists, engineers and physicists. We do fundamental research in coral, we work in all of these spaces. We don't do forestry, but the money that is available now to get our technical expertise to solve these problems is immense. So the US just invested $2 trillion in biomanufacturing. UK's invested, EU's invested, there's public investment. So the opportunities are there. So in summaries, I think we have the technology to use biogenic carbon to fix and save the planet. I think construction industry is an absolutely key part of this because it's going to store it for 20, 30 years. The advanced biomanufacturing technology exists. Estonium is going to incentivise it. And I think the opportunities for us as scientists is really immense to get into this space and help solve the problems of the planet. With that, I thank you all for your time and attention. Unfortunately, I'm a bureaucrat these days, but these are all the clever people that did all the science that helped me understand what I'm doing. So, thank you.